So can you see my slides?
Yes, yes, I can see. Yeah, we can see, Eric. Yeah,
So I
please.
start.
Yeah, please start. Yeah.
Okay, thanks again for having me. This course is mostly an introduction to data and AI and different techniques that we have for representing and processing data. We'll talk a bit about classification and clustering in the first lecture. I hope you all guys all have the slides. If not, there will be a link later. These are again some pictures from 2018 when I was at IIT Patna in person. This time, unfortunately, we have to do this online, so I cannot get my scarf and other nice gifts that I got last time. But yeah, it's as if I was there in a sense that this is a workshop for all of you to get introduced to data and AI and NLP as well. But I hope that we can have also some discussions later, either after lectures or even after the workshop. You can always contact me if you are around NTU and Singapore. You can come and find me at my office. You just have to look for the colorful hourglass and you can send me an email. You can also instant message me on Instagram. We are actually expanding. We became the College of Computing and Data Science just last year. Before that, we were the School of Computer Science and Engineering, and we are actively hiring. So if you are interested in joining us or know someone who could, please let me know. So this is our team. It's about 20 people, 2 postdocs, um, a dozen PhD students, and a few more interns. You can check out this link who we are and what we are doing. Again, if you want to collaborate with us on any effective computing topic. Here on the slides, you also have some links on how to apply for a PhD at NTU or even like for an internship. We also have 2 spin-offs. One is about sentiment analysis, the other about finance. So this is also a way for us to collaborate. So this is the overall overview of this workshop. It's 5 lectures. All lectures have different number of slides, so we'll just go as we just see as we go. It's not strictly 2 hours per lecture, so we'll see. I guess we are taking a break every hour, so I'm also flexible anytime any of you wants to stop me to ask for questions. I'm also fine with that. It's always nice to take a break. So yeah, today we're mostly talking about data representation, classification, clustering. I apologize to those of you who already know these things, but I want to start with some basics for those that have never been exposed to data analysis, so that we are all on the same page before we start talking about AI. And this is the book that where most of the contents are from. This is a textbook. Okay, sorry, I have to quit my email, otherwise it keeps bothering us with sounds. Okay, done. So yeah, this is quite recent. It was published just end of last year, so only a few months ago, and this is where you can find more details. The slides of this course are enough, of course, to take the final exam, but if you want to know more and you are also doing a project on AI and NLP, then I strongly suggest you that you download the book. I believe that with IIT Patna account, you can download this for free. So you can also buy the hard copy. It's very nice, but the soft copy is enough. And here you have some pointers on what's available on the book. There's also some code. I won't be talking much about code in this course, but for those of you who wants to get their hands dirty and code in Python to develop some of the techniques and modules that we'll see, you can also do that. So here's the link to the slides. The slides are for educational purposes only, so please do not post them on your blog or on your Twitter. Just it's just FYI. And
Hello, sir.
yes.
Sir, your screen is not visible anymore.
Oh no.
Just-
Thanks for telling me. Oh yeah, I have to share again. Wow. Okay. Yeah, so I don't know where the slides that you didn't see, but supposedly you have these slides. This is a link to the slides. Centik.net is my website that you can also very welcome to navigate. And then 2025 GAN.pdf is where you have this set of slides. And what I was mentioning earlier was this book. And so here you have the QR code and also the link. And here again is a list of things that you can find on this book, even some tutorials, quizzes, assignments, and so on. So, okay, let's start. First, as I mentioned earlier, we are going to be talking about data first. So data, as you have heard, is the new oil and AI is the new engine. And this is very much true because all these new AI techniques are very much data hungry. So this is a bit different from what was happening just maybe a decade ago. In fact, for example, when I was a PhD student, it was very easy to find data and not so much code. People were very much protective of their code. And now it's kind of the opposite. If you think about it, even Google gives you their codes because they know that without the amount of data they have, you have no chance at replicating their results. And data actually is also a matter of discussion in terms of the amount of data, the volume of data we are producing, and the pace of this production. Sorry, I didn't get. Was that the question, or is there still problem? I didn't understand. Sorry, you can't hear me properly.
Yeah, pardon. From participants, are you saying anything to Professor Eric?
Maybe they
Ratnesh,
accidentally on the mic, or was that a question? Okay, maybe they just accidentally on the mic. I'll continue, but then if you have questions, feel free to ask me anytime. You can also use the chat to type the question if you don't want to ask by voice. So I was saying that there's also discussions on how this data is going to be represented. There are some papers that as a solution to the huge amount of data that we produce, they propose that we save data in a DNA-like structure. But as you know, it's not just a problem of volume, it's also a problem of variety. The fact that data comes in so many different formats, velocity also that comes at very high speed, and finally veracity, all the problem that people talk about online about fake news and how much you can basically trust your data source. But what is really data? So this course will be a lot about text data, NLP, but then as we'll see later when we'll talk about embeddings, we actually have to translate this data into a numerical form that can be processed by our computers and then translate it back to text. So that's not probably exactly what's happening in our brain, but that's the best thing that we can do so far. And it's a bit similar to the Fourier transform, if any of you is familiar with it. You go from time domain to frequency domain to do some calculations, and then back to the time domain. So in data processing today, this is also what's happening. We have to translate documents or web pages or novels or anything into numerical form, do some processing, and then back to texts. So there are three main kinds of data representation with all nuances and particularities, but mostly you could say there are these three main ways to represent data. The first way is the simplest, and it's about just encoding presence. So if I have a vocabulary of words, then given a sentence like this, S1, I just put one, and whenever the word that I have in my dictionary does appear in the sentence, so that's why the first number is 1, and 0 when it doesn't. So knowledge, which is the second item in my dictionary, does not appear in the sentence. And so that's how I have my Boolean vector, a vector made of just ones and zeros. And this is the simplest way. That doesn't mean that you shouldn't do it today. There are still, for simpler application, there are still one-hot encoding algorithms that perform processing. One example, if you're searching for a document on your Mac, Spotlight, for example, uses one-hot encoding to find document. That obviously works well for something that you know exists in your computer, but not so good for web search. For bigger documents and web search, as many of you probably know, is the model that have been used a lot before deep learning became popular was the bag of word model, or TF-IDF. So basically here, instead of having ones and zeros, we were actually counting how many times each word appears in a document. And it's called bag of words because we were not encoding the sequence of words in this representation. So it's like, was really like a bag of words, because you just throw all the words in there, you count how many times they appear, and then you do classification, like, for example, sentiment analysis classification based on that. The thing that is everybody's using now is based on transformers, deep learning, that instead implements the continuous bag of words. So you're not just counting frequency, but you're also looking at the sequence of words. We'll look at this later when we talk about deep neural networks and word embeddings. But let's briefly have a few minutes crash course on the first two. So this is important because we can see how we can very simply build a sample of a vector space model. So here what I did is, again, just a Boolean model. I have some of the plays of Shakespeare's on the columns, and then on the rows, I have the words that make up these novels. Of course, I don't have all the words here. For simplicity, I stop at 7. So this, you could say, is a Boolean 7-dimensional vector space. Why? Because then, as we'll see later, I can actually visualize and plot these documents into this 7-dimensional vector space based on these coordinates. And TF-IDF, or bag of words, goes beyond encoding presence and absence because, as we said, also counts the frequency. Then the actual way to calculate this is through a TF-IDF weight. We don't just blindly count how many times this happens, but this is not the focus of this course. You can look up how TF-IDF works, but the bottom line is that in the end, you have that your documents are represented using these coordinates, these weights, in this case, TF-IDF weights that in this specific example have not been normalized yet, in using 7 dimensions. Again, why 7? Because in this simple example, we decided to use only 7 of the words. But in reality, I'll have many more of these. And the way this works is that, for example, the Tempest doesn't contain any of the 5 words that are here, Antony, Brutus, Caesar, Calpurnian, Cleopatra, but contains some of Mercy and Worcester. So this is useful for many different reasons, because then you can calculate a distance or a similarity between two documents, and this can be used for information retrieval, for sentiment analysis, and so on. So what does it mean to build that vector space? When I say maybe 7 dimensions, some of you may think, what does that even mean, to how to build something in 7 dimensions? But actually, that's not anything difficult. You can think when you represent a point in one dimension, you're working on a line. Then when you're in 2-dimension, you need 2 coordinates. And finally, when you go to 3-dimension, you need 3 coordinates to represent a data point or a vector. If you think of this document as an arrow that goes from the origin of the vector space to the point. And when you add more dimensions, actually, it's not a big deal for our computers. For us, it's not easy to think of representing something beyond 3 dimensions. But for our computers, it's no problem to work with hundreds or even thousands of dimensions. So here you have another example of a few documents that I represent in a 3D vector space. So 3D means what? That I'm only using 3 words to represent these documents: color, vehicle, and motion. And then depending on the words and the number of times that each of these words is mentioned in the document, I will have different arrows. So these arrows again represent my documents, because these documents are actually, once again, points in this 3D vector space. But because of how we'll calculate similarity later, it's also good to represent them as arrows that go from the center, the origin of the space, to the point. And here, this is a useful image to understand why we are not using the Euclidean distance, but we're using the cosine similarity. If I have a query Q and I want to find an answer to this query, D2 is probably the correct answer, the correct document. You can think of this as a Google search. So document 2 is definitely the most relevant because of the terms that it contains. So here we're in even simpler situation. Instead of 3D, we are just in 2D, and our dimensions are simply jealous and gossip. So most likely this query is jealous gossip, and D2 is the correct answer because it contains maybe a good quantity of these 2 words. If I calculate the Euclidean distance between this point and this point, I get probably that it's bigger than the Euclidean distance between these 2. And that's exactly why in these vector spaces, we don't use Euclidean distance, but instead we look at the angle between vectors. So when I have a 0 angle, it means that the 2 documents are equivalent, and I can see this by copy pasting the same document D into itself, and then I have D prime. The new vector that represents the new document will be longer, will be double if I copy paste the same on itself twice, but the direction will be the same. So this is the best example to understand why we look at angles and not Euclidean distance, because if you calculate the Euclidean distance between these 2, it will be some number, while the cosine similarity will be 1, because the angle between these 2 documents, which are the same document in fact, is 0. So here again, I don't want to spend too much time on this. You can look it up if you are interested. So this is the formula to calculate the cosine similarity between any query Q and any document D in any dimension, in V dimensions. And when you normalize your space, actually, it's very easy. It's just a scalar product. You just have to multiply each of the dimensions and then sum them up all together to get this sort of similarity score that goes between 0 and 1, where 0 is completely different, to 1, which means that they are identical. So in fact, when we are building, for example, word embeddings or some of those models that we'll see later, like Word2Vec, as you keep adding more documents, the dimensionality of the space increases. And so we need to use some dimensionality reduction technique to squeeze the space into a smaller space. We can do this because then the distances between these documents in this reduced space will be equivalent. And you can use different techniques to do this, like in one of our last works, we used random projections, but the most common thing to use is, the easiest thing to use is SVD, singular value decomposition. And this is a very interesting mathematical quality of matrices, so that I can actually factorize any matrix X into these three matrices. So this is the same as doing, for example, 6 equal to 3 multiplied by 2. So I'm just decomposing the matrix into this three. And what's interesting is that the one in the middle, the sigma, where the singular values are stored, is a diagonal matrix. So everything in this top left corner and bottom left and top right are zeros. I only have the singular values in the diagonal. And what's really interesting about this is that they are also ordered in terms of importance. So you have that the most significant singular value is at the top left corner, while these other singular values at the bottom right are actually values that I can discard. And this is how I can do dimensionality reduction of my matrix X, which is what? My vector space. So I can cut off some of these, recalculate the matrix. I will get a new matrix, which is not the same, but equivalent with fewer dimensions. So it's a bit like taking a picture of something, right? If you take a picture of an object in 3D, then it's like you are projecting the image of this object in 2D. And here is an example of how first SVD algorithm was applied to do the JPEG size reduction. So in the original picture, you have all the 512 singular values. Here I throw away half of them, which means that I remove all the half of the singular values here in the bottom right corner, recalculate the matrix to get, again, to reproduce the picture. And as you can see, it's almost equivalent. Like to the human eye, there's not much difference, but I saved a lot of space because now I have a picture that is half the size of what I had before in terms of the dimensionality or space occupied by this picture. And here I continue to cut off half of the singular values. And as you can see, as if I cut away too much, the image deteriorates. So another important topic here, when you do dimensionality reduction, when you compress a big space into a smaller one, for example, to publish a set of embeddings, you have to find the best trade-off between resizing without cutting too much information. Why? Because then if I'm projecting a space that is made of 1000 dimensions into just, for example, 3 dimensions, every data point will be so near to each other that it will be impossible to distinguish. So this is how a vector space model can look like. This is a snapshot actually of affective space, which was our work from more than 10 years ago, in which we built a vector space for affective computing for words and multi-word expressions. And here we decided that the best trade-off was 100 dimension. But if you take, for example, Word2Vec, I think it's 300 dimensions. So it also depends on the amount of data that you're working with and also the sparsity in the space. As long as you have every data point that is far enough from each other, then it's okay to continue reducing the space. So generally, when you build a vector space, these data points that you can see using some visualization tools should be your documents, but it can also be an image, a video, whatever is the data that you're working with. In this specific example, it was none of these. It was just a natural language concept. So talking about words or multi-word expressions like this, learn subjects. And then here, finally, by calculating the cosine similarity between these points, or even if you want the Euclidean distance, you can decide whether this concept is similar to this concept, or even perform classification. Because, for example, here, what a property that we realize heuristical is that in this snapshot, again, this is a 2D representation of a 100-dimensional vector space. More or less, you can see that in the bottom left corner, you have positive concepts, where in the top right corner, you have negative ones. So how to do classification in this vector space model? You can use different techniques. You can use a supervised learning approach or unsupervised. So in the next few slides, we're just quickly gonna see how to do that. Again, this is just for your information. If you want to know more about this, you have to go and read some books on how to do this in more detail. So let's say that we have these few documents. I don't know how many are they, maybe 20. And I have to classify them according to these three classes. So these documents have already been labeled by someone. So I know that, for example, this is a cluster of the class environment. This is social, this is governance. So one thing that I can do to classify any new document that I get, in theory, like if I get this new document, then the question is, which class does this document belongs to? Or if I'm doing information retrieval and this is a query, then which are the documents that I should retrieve? I could use something to separate the space. So I could use, if I have two classes, for example, I could use a naive Bayes classifier to have a linear separator that cuts the space into two halves, or I could think of something like calculating a centroid. What is a centroid? Is you can think of a centroid as the center of mass or center of gravity of the cluster. So if I take maybe this black cluster that represents governance, if I were to calculate the centroid of this class, would probably be a point here in the center of this cluster. So why do I do this? Because then when I get a query, I can calculate the distance between each of the three centroids that represent these three clusters to decide to which class this document or query or image or video or data belongs to. So this is how I would say 90% of computer science works. We represent data in these vector spaces, and then we use either Euclidean distance, like we mentioned before, or better cosine similarity using TF-IDF weights to calculate the angle between these vectors that represent my data. So there are, again, different ways to perform this kind of classifications depending on what's your goal. When you have to predict the future, maybe you are trying to do stock market prediction, then maybe in those cases you use regression or least square errors. If you want to use like PCA or SVD, like we just mentioned in the previous slides, then you do discriminant analysis, which is again about projecting your data into a smaller space. Prototype methods are also very useful. We're going to see them later when we talk about KNN. Support vector, also very useful way of classifying data, especially when I have to do binary classification. This has been the state of the art for more than 10 years before neural networks became popular again. And then there are a few more. The easiest is just to calculate a probability of likelihood, like you do when you calculate a posterior probability using the Bayes rule. That's why it's called the naive Bayes classifier. So if I have to define whether a document belongs to class C or not, I just represent the document as a bag of words. So all these X's are the words that make up document D. And then I have to calculate two probability. Probability number one is that the document belongs to class C. Probability number two is that the document does not belong to the class. How do I do this? I don't know how to calculate this probability. I use the Bayes rule. And then because I'm calculating a max, because I have, once I calculate these two probabilities that I just mentioned, of course, I will have to take the biggest one because I'm calculating the probability of document D to belong to the class or not belong to the class. So of course, I'm going to take the bigger one. And that's why I only care about the denominator. And here I use this assumption that actually is very naive. That's why it's called naive Bayes, that all the words that make up the documents actually are independent from each other. And that's why I can break up this difficult probability into smaller ones. All these small probabilities are the probabilities of each word to belong to class C, and finally multiplied by the probability of the class, which is simply how many documents I have for the class and not for the class. So again, here just a very brief introduction, but you can read more materials on this, and this is a very simple classification algorithm, but you can still use if you have a relatively simple data set, or you don't have the luxury to use a neural network. It's totally fine to use naive Bayes classifier for some applications. The other one is the KNN, where instead of calculating the distances between the new document and the three centroids, I just look at the neighbors. So KNN stands for K nearest neighbors. The K is the number of neighbors that I am considering, which I also have to define a priori depending on my data, depending on some heuristics. So in this simple example, I have a 6NN, K equal to 6. So what I'm doing is calculating the probability of this document to belong to each class based on the number of neighbors that I get. So I can calculate, for example, again, a cosine similarity or a Euclidean distance to find out, for example, that 5 out of 6 neighbors belong to the class environment, and hence I may classify this new document as belonging to the class environment. And this is a very simple yet effective algorithm that you can use, and it's very much it's different from naive Bayes, because naive Bayes looks at the big picture while KNN is more specific. So in this very simple picture, you can see 3 lines. The yellow line is the one that I would draw if I have to separate the two classes, like you have the full circle and empty circle class. But arithmetically, I have to build some model that can do that instead of me drawing manually this yellow line. The red line would be the naive Bayes classification, because as I mentioned, is like a linear separator that cuts my space into 2 halves based on the probability of my training data. And here again, we are seeing this example in 2D as a picture, but in reality, this line, this linear separator is what is a hyperplane in 3 or more dimensions that once again, it's cutting my space into 2 halves. And instead, when I use KNN, I'm just looking at the neighbors. So I have this white line instead that is more is taking into account more the sparsity, the density of the data. So in this specific example, of course, if you ask me, it would be better to use KNN, but it's not always the case. When the data is well behaved, it's better to use naive Bayes so that you can linearly separate the data. But nonetheless, this is an interesting topic because it introduces you to the concept of variance and bias. So KNN and naive Bayes are two very good example of what actually we should avoid in general. Why? Because KNN has high variance and low bias. So that means that basically I am overlearning. This is also called overfitting. It's a bit like if I'm building a system to distinguish, to find phones in an image, and I'm only using, for example, an iPhone as my data training. This system will only learn to recognize a phone as an iPhone. So if I show another phone, it will say, no, this is not a phone. And that's a mistake. That's when I have high variance. The other extreme is when I have low variance and high bias, like in the naive Bayes. And in the example of maybe a botanist, it would be something like anything that is green can be classified as a tree. So I don't want to be in any of these two situations in general, and that's why we're using neural networks these days to solve this classification problem. So as I mentioned, when you have high bias, you have underfitting, and when you have high variance, you overfitting, like overlearning. You want to find a good compromise. So that's why people started looking at neural networks, because they can model also the nonlinearities of these spaces. And as we proceeded, then as we'll talk in lecture 2, we went from feed-forward neural networks to convolutional neural networks, and later on transformers. But this is exactly why we are using neural networks. But once again, it doesn't mean that we have to use neural networks all the times. If I have a very small data set, for example, I cannot feed it to a convolutional neural network because, as we mentioned in the very beginning, these new algorithms are very data hungry. I need to have a lot of data. But sometimes it's also for other reasons. Like if I can solve the problem just by using KNN or naive Bayes, then why bothering training a neural network, right? Also because naive Bayes and KNN, they can classify very fast. But we'll talk about this later in lecture 2 when we talk about neural networks. Before I conclude, I want to talk about SVM as well. Many of you probably know this already. SVM is still used today for some binary classification tasks, sometimes together with neural networks. And here the problem is we want to find, once again, the best linear separator between two clusters, between two classes. So here intuitively you can see that if I want to separate class red from blue, it's better to use the green line than the black one, right? But how do I formalize this? How do I make a mathematical model out of this? Actually, and that's what SVM does. Vapnik came up with this idea of finding the one with the biggest or the fattest separator between the two classes. So this, for example, is too narrow and it's not a good separator, while this is a good separator. How do I find this separator? I have to maximize the space between the two support vectors. What are the support vectors? Are those vectors or documents at the border, the ones that are more representative, because then for anything that falls in between, I need to have a separator to classify it as class red or blue. So here, in the next slide, I have some of the formulae that are used to calculate this raw and maximize it so that you can apply SVM. But again, that's not the focus of this course. I put this here so any of you who is interested can look and find more details. And sometimes you don't even need to know exactly how SVM works, as long as you know how to interpret the results. In fact, there are many libraries like Python libraries or MATLAB and many more that you can use to perform SVM. Of course, SVM comes with some issues. The first is that if the space is not linearly separable, then SVM will not work. And another big limitation is that it's meant for binary classification. So usually just for two classes. What do I do if I really want to apply SVM and I have three classes like before we had the ESG class? I can do a one versus all classification. So I take one class at the time and I do a separator between this class and the other two, and then I repeat for all classes. So to conclude this first lecture, I also have to talk a bit about clustering or unsupervised classification. What does that mean? It means that I don't have the luxury to have labels. So in deep learning, they often say that there's no free lunch. So deep learning works very well, but it requires a lot of labeled data. Labeled data means what? I have to basically pay someone to tell me whether an image belongs to this class or that class. And so what if I don't have those labels? Can I do something? And that's what clustering does. So here you have another example of a very simple 2D space in which I have some data points, no classes given. That's why these points are empty. And I have to cluster them. So visually, now I can see that there are three clusters here, and I could like circle out and separate. But sometimes you don't have the luxury to visualize data in this way. Maybe you have a 300-dimensional vector space. How to see the data in this way? Well, you don't have to see it. You can use some mathematical models to perform clustering. So again, we are using the concept of centroid. Centroid is going to calculate the gravity mass of the center of gravity of each cluster. So for example, for this cluster here in the top right corner, the center is probably going to be something somewhere here. And then I can use some algorithms to do this. One famous algorithm, simple but very effective, is k-means. So once again, here I have some data points with no classes. I pick two random seeds. And as you can see, this choice is bad, actually, because supposedly I would want to have one seed from the left cluster and one from the right. But the power of k-means is that it also works well when I don't pick the seeds properly. So what do I do? First, I pick two random seeds. Then I assign each of the document to one of the seeds based on their, again, Euclidean distance or cosine similarity. And so that's what happens next. I reassign the clusters. Then I can calculate the centroid. So based on this distribution of the two classes, red and blue, I calculate two centroids. So this, for example, is the centroid of the class red. Why? Because it falls in between all these red dots. So next, I can actually try to reassign the clusters again according to the centroid. So here, if you look at this point, for example, when I reassign according to the centroid, it will become blue because it's nearer to this centroid than this one. Then I recompute the centroid, and if I try to reassign the clusters, nothing happens. And that's how the algorithm converges. So this is very simple yet effective way to do what? To cluster data in a multi-dimensional vector space. So even if you don't have any classes, any labels, you can still understand where you have different clusters in your vector space. So the example that we just saw was in 2D, but then of course, when you go in 3D, you have clusters that look a bit like this. And then as you move forward and use more dimensions, you have similar situations, and k-means also works well in many dimensions. So a very good way, for example, if you have a lot of documents with a lot of words, so you end up with many hundreds or maybe even thousands dimensional space, you can use k-means to see which groups of documents are more similar to each other, which document belongs to each cluster, even though you don't have any labels about these documents, if nobody told you which classes these documents belong to. And again, here I don't want to spend too much time on this because I prefer to talk about AI in the next lecture, but there are also here many other different ways to perform clustering. One that we used a lot in the past, before we started using deep learning, was the k-medoids, which is very similar to k-means, but k-means, as we saw many times, when you calculate the centroid, it just gives you a point in the middle of the space. K-medoids uses one representative document or data point in the space. So the way it works is that you first calculate the centroid and then you take the nearest data point so that you can look inside this document or image or video to understand why it is representative of this cluster. Then there are a lot of other optimization techniques that you can do, like in this specific example, maybe this point here is a outlier that I may want to remove so that I can better calculate the centroid or the k-medoid. But these are things that you can look on your own when you are, if you are interested in performing unsupervised learning. So this is, if I'm not wrong, the last slide of lecture one that summarizes the differences between classification and clustering. So in this first lecture, we saw what is data, how we can represent it in three different ways, although we haven't seen word embeddings yet, and then what to do with this data for classification and clustering. So I'm happy to take any questions if you have any. Otherwise, we can probably take a break. I don't know what's the schedule like?
Yeah. So from the audience, from the participants, you have any query or question, you can ask, or if you want to discuss something. Yeah, anyone?
BT has a question. He raised his hand.
Yeah, please go ahead.
Vivek.
Hello, Harry. Thank you for your
Hi.
fantastic talk. And so you were talking about factorizing the matrix and then discarding singular value and rebuilding the matrix in order to figure out maybe solving a problem. So
Yes.
Is it a generic method or applicable across all the domains, or do you think it is only specific to one particular task? Can I generalize this method everywhere?
Yes, this is something that you can do for any kind of data, because then, as we said in the very beginning, when we are working with data, no matter if this is a document or an image or a video, I have to go into the numerical domain to represent it in one of those vector spaces that we saw before, like this one. Here's a snapshot of a 100-dimensional vector space of concepts. But these points in the space, depending on how you build the space, they can be anything from documents to queries to images to videos. And this is a very generic way of reducing the dimensionality of the vector space that is a mathematical property of matrices. It doesn't take into account absolutely any domain-specific information. So this is applicable to any kind of data. The only thing that will change depending on the domain and the data is how much of these singular values can I throw away? Because in this case, when I'm talking about images, you can cut away a lot. Like even this picture here that only uses the first 64 out of 512 singular values is still good enough. But because maybe it's an image and our eye cannot appreciate the differences and the nuances required to really appreciate this image. But maybe if I'm working with video, it will be a different thing. A video that of which I cut away so many singular value, maybe it will turn out to be a very low quality video, or even if I'm working with text, maybe things will not work as well as expected. So the answer to your question is yes and no. It's a general technique that you can use for any data, but depending on the domain, the amount of singular values that I can remove can vary. It depends on the domain and also the data, how much data you have, the probability density of the data, and so on.
Thank you so much.
No problem.
Yeah, thank you, Eric. So anyone else have any question for this particular session? You can raise your hand or you can type the question if you want. I guess there is no question, right? So yeah, so we can maybe we can wrap this particular session. So again, Gunjan, when we will start the next session?
It is at 2:30 Indian time, sir.
Okay, so Professor Eric will start at 2:30 afternoon. Okay, maybe next session, right? That is lecture 2. Or if you want to continue it now,
I don't know, up to you. I'm fine.
let it, because it is already 12:30.
No, sorry, it's time for lunch for you.
Yes, yes, yes.
Okay,
So let
yeah.
us have a break
Because here it's 3 p.m. So, but then it makes sense for you to take a break now to have lunch.
Yes.
So
let us do one thing. Let us have a break for maybe 2 hours or so, right? Then maybe at IS3 2:30 we'll be starting the next session. Is it fine?
1 hour? I would prefer 1 hour if possible.
1 hour. That's fine. That's fine. I think if the participants are ready, 5:30. So can we start at 1:30, Gunjan?
Sir, you may start, but as per the schedule, the next lecture will be at 2:30.
Okay, 2:30 to how long it is?
It is 3:30, sir. By
Okay,
Srikant, sir. Yeah.
Sir, today's next onwards, there will be tutorials. I'm Srikant, sir, actually.
Okay, okay, hello. So I think
Yeah.
that means there is no, you send me share the lectures details with me. Okay. I think Professor Eric's, he do not have any session today, or he has?
No. No.
No,
Eric sir
no.
has only one, and that's completed. Yes, sir.
Okay.
Yeah,
Great.
from tomorrow will be different, but today it's like this. Okay, so I'm done for the day. I will see you tomorrow.
Yeah. So thank you, Professor Eric, once again for your insightful session. So we'll be connecting you for tomorrow. Again, we'll be listening a lot from you. Okay, thanks a lot.
And if any of you have questions after you maybe look again at the slides, digest the slides, you can email me or you can ask me again tomorrow, and also advice on whether if you guys already knew all these things, so I have to go faster. That's also, I'm also getting happy to get this kind of comments.
Okay, thank you, Professor Eric. So Gunjan, please start the next session. I'll be there also probably. So at 2:30.
Yes, sir. Please, sir. Thank you, sir.
Thanks a lot.
See you tomorrow.